All right, so let's start trying to go through this here. So first of all, I got a multiplication, an addition, and a division. Which one of these operations am I going to have to do first?
Left to right is multiplication.
So I'm going to have to do the multiplication or the division first. Either one of these would be fine, but I definitely have to save that addition for last. Okay? So step one, I'm just going to punch it into my calculator. My calculator is going to give me 1,211.345. But now we got to apply our rules for sig figs, and for a multiplication problem, is that our counting sig fig rules or our position sig fig rules? Counting. All right, so that means I'm going to have to pay attention to the number of sig figs in each of my inputs. The 31.10 has 4. The 38.950 has 5. So then my answer has just 4, right? Whichever number is less. And I'm just going to mark it with a bar. I'm not going to round yet because I need to go take that number and do more math with it, right? So I'm just going to use this bar notation here to keep track of where my sig fig is in that number. All right, so now we're going to move on to the next one here, the division portion of this problem. Again, just going to punch it into my calculator. 392.59259. All right. And I'm not going to bother writing down every digit my calculator gives me. In general, good rule of thumb is you need at least 3 digits beyond where the sig fig is in the number. All right. So anyways, I'm just going to sort of arbitrarily stop there. This is another counting rule here, right? So I need to pay attention to the number of sig figs in each of my inputs. How many sig figs are there in that 1060 number? There's only 3. Why doesn't that last 0 count? No decimal in the number. And then 2.7, all non-zero, so that just has 2. So that means I need to mark my second sig fig in this number here. All right, so now I can move on to the addition portion. Okay, but addition now has a different set of rules. It's not counting, it's going to be a position rule. So remember, the way we're going to do this, we're going to line it up with the decimal. I'm going to rewrite this here. That 1211.345. Again, mark that ones place with a bar. Add that 392. I'm going to mark that sig fig with a bar. I'm going to choose a different color. Okay, so now we have our addition problem here. And right off the bat, before I even do the math here, I can tell where the sig fig in my answer should be, right? We're going to look at these two different positions. I have this green column right here, the tenths place, and I have this red column right here, the ones place. Where's the sig fig in my answer going to be? Green or red?
Green.
Green, the one that's further to the left, right? So that's tens place. So now I'm going to perform my actual addition. And again, this is where your nice calculator is really handy. Even though I only wrote down a few digits after that decimal place, I'm going to go up and copy that number. So there is 0 rounding error involved, right? I'm going to grab that exact number from my previous calculation. I got to actually add an add sign in there. There we go. Cool. So my answer here is now 1603. Again, that 0, I put a few decimal places on there, but clearly we're going to round before that. Okay, so now I have to round this number to the tens place here. Is it going to round up or down? It's going to round down. So that is 1600, and I'm done. What's wrong with that number as written? It's only got 2 sig figs, right? And actually, I can't just put a decimal here because then it would have 4, right? So remember, this is this kind of weird situation. It won't happen very often at all, but I wanted to do another example. There are 2 ways that we can indicate that that tens place is significant. One is to just simply put a bar over it, right? It's rounded. We're going to mark it significant with that bar. The other way, and we'll review this a little bit more next week when we introduce the mole, is what's called scientific notation. So 1.60 times 10 to the 3. Both of these would be perfectly sufficient ways to represent that same number. Okay? But this is my final answer for this complex calculation, rounded to the correct number of significant digits. All right? Again, you got to perform each operation separately so you can keep track of your sig figs. And again, that's the case because we have these compound operations, meaning we have a problem that has both addition, subtraction, and multiplication division, which has two different sets of rules. Okay. So last thing we need to do before we can move on for sig figs, from sig figs rather, there's two more concepts here. The one is the concept of an exact number. All right, so some numbers are not measurements. And are considered exact. All right, so let me just give you a very simple example here. We have about 32 people in this room right here, right? Is there maybe 32.1 people? Is there maybe 31.9? No, that 32 is an exact number. There are exactly 32 people in there. There's no wiggle room about that 32 like there would be if we say measured the length of this desk, right? So that would be considered an exact number. And we can spot exact numbers because they always fall into these two categories. One is their count, just like the example that I just gave here, right? So counts are always exact. And the other way that we're going to see it, quite often actually, is with regard to our unit conversions and numbers that are defined to be exact. All right, so what we would call definitions. Okay, so just to give examples, again, 32 people, that's an example of a count of an exact number, all right? But in terms of a definition, what do I mean by that? I want everybody to flip over their constants page here to our conversion factors. All right, we got a bunch of different conversion factors that will help convert from one set of units to another. If we go down under distance, just like 4 or 5 lines down, and we have 1 inch is 2.54 centimeters exactly. And if you looked at that 2.54, you'd be very tempted to say that there are 3 sig figs associated with that number. But this is a definition, so it is exact. It turns out that an inch is defined as 2.54 centimeters. When everybody got together and said, what should an inch be? They said it's going to be exactly 2.54 centimeters, right? So it's this definition that we put on there. And we'll see that a lot of our units are defined that way, all right? So definitions as well as counts are exact. And actually, exact numbers are quite nice because exact numbers will never limit our sig figs in a calculation. You basically get to ignore those terms in your math problem when you're figuring out your sig figs. And we'll see a bunch of examples in this because we're going to get to using this page here by the end of the day today. All right? Cool. So then the last thing we're going to talk about is this plus minus notation. Or what's also called precision. All right, so first of all, let's just do an example here. We have a number like 3.00. Okay? Based on looking at that number, what can we say about that number in terms of the number of sig figs it has? It's got 3 sig figs, right? Those trailing zeros count. You can also represent this exact same thing using this precision notation, okay? When you say that a number has 3 sig figs, it's implied that it's 3.00 plus or minus 0.01. Where in that plus or minus, the thing over here called the precision same place as your last sig fig. All right, in a measurement, that last sig fig, we've just been calling it this last sig fig this whole time. We've indicated that with a bar. It's also got another special name called an estimated digit. When you make a measurement like 3.00, you're saying you are super confident there's a 3 in the ones place. You're confident that there's a 0 in the tenths place. But that hundredths place is a little squishy. We're not super duper confident of the last sig fig in our measurement, right? So that is our estimated digit. And again, we can represent that using that, using that plus or minus notation. Oh, geez. All right. So let's say that we're given something like 45.369, but we're told that the precision is only 0.1. That means that our estimated digit is in that tenths place. So we can't have all those extra digits on there. That 6 and that 9 are basically completely made up. We're not confident about those at all. All right, so in this case, we would have to round this number to the correct number of sig figs. Given my little marking here, that would just be 45.4. Okay, we're going to see this sort of representation of sig figs with our glassware in the lab a lot. And so when we get into using our glassware next week, we'll see this kind of representation over and over again. You'll have a bottle that says 25 mils, but then it will tell you what the precision is, and that tells you how many decimal places you need to have when you're using that instrument. All right, so real quick, let's just practice rounding to the indicated precision here. Okay, we can leave our example up. All right, I'm going to give you 2 more examples that you're going to do for me. Sorry, organization. All right. Oops. All right, so take these from our precision notation to just our standard notation for sig figs. All right, so in our first example here, our precision is this hundredths. So that means I need to mark that hundredths position, right? 2 decimal places in my precision. I need to round to 2 decimal places, or simply just 0.03. In our next example here, the precision is 10, right? So that means I'm going to mark the tens position in this number, which is what value? The 5. Okay? And remember, don't change the number. We don't want to put 45. We want to make sure that 4 is in the hundreds place. The 5 is in the tens, so that would be 450. All right, and here I have 50, but plus or minus 0.001, right? My precision is all the way in that thousandths place. So I need to put more digits on the end of that measurement in order to record it to the correct number of sig figs. All right, and this is a great example of what you will see printed on glassware, right? There will be a number, that's the milliliters, the target value, whatever it may be, but then it also gives you the precision, which means that when you record that data, you need to make sure to record it with that correct number of sig figs, right? That 50 looks like it only has 1. You use that piece of glassware. No, 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 you got 5 sig figs out of there. Cool. All right, so this is a chemistry class, so we should probably start talking about atoms and elements and all that other crap, right? Instead of just doing math all the time. Okay, cool. So let's go back and review here kind of the basis of chemistry. We're going to start at the beginning, talk about the anatomy of an atom. Okay, and before we start talking specifically about atoms, it's important to just kind of take a step back and understand like why chemistry exists. Why is chemistry a science that's taught in all the high schools around and all these colleges? It's one of our 3 major sciences. So why? Why has it stood the test of time here? Chemistry has one major win under its belt, one huge success as a way to explain the world around us, and that is that the world around us is made of atoms. And you and I always grew up at a time where chemistry existed, where we all kind of already knew that, or at least people did, and that's what we were taught from a very young age. But there was a time not too long ago, 300-400 years ago, where that was not well understood or even believed at all. Some of the very smartest people in the world believed that the best explanation for the world around us was kind of a very religious-based explanation, right? It was all about God and all that other stuff. That's how the world around us worked. And then we had this scientific revolution where people were like, maybe we should start testing these theories instead of just spitballing here. So along came people who proposed that the world around us was all made of atoms, and ding ding, they hit it on the head, turned out to be correct, right? Everything around us is made of these tiny little building blocks. So great, they established that, and then they got even better technology, and they established that each one of these tiny little building blocks is actually composed of 3 subatomic particles, right? So every atom around us is made of 3 different particles, all right? We have the proton, as well as the neutron. And both of them live in the very center of the atom, which we call the nucleus. All right, so protons live in the nucleus. Neutrons also live in the nucleus. And then there's a third one that does not live in the very center of the atom. It actually is zipping around on the outside. And these are what we call electrons. Right? So you're all made of atoms. This table's made of atoms. The air's made of atoms. All of those atoms are comprised of these 3 subatomic particles. All right? 2 of which live in the very center of those atoms. And the last one is kind of zipping around on the outside, always in motion, all right? So these three different subatomic particles have very different properties. So we're going to make a little table here. All right, we discussed where they live, but there are two other important differences that they share. Okay, the first one is the mass. There's a big difference between the mass of these three subatomic particles. Protons and neutrons are way more massive than electrons. We give the mass of a proton at about 1 AMU, atomic mass unit. A neutron has the same mass, 1 AMU. But an electron is super light, almost zero. Actually, it's more like 0.005 AMU, but incredibly light compared to the other two subatomic particles, which means that most of the mass of an atom lives just in that very center. The electrons that decorate the outside are very light. They're moving very fast. And another big difference between these three subatomic particles is this concept that arises from physics called charge. Let's see who remembers from Chem3A. What is the charge of a proton? Positive, and in fact, specifically +1. All right, not just a positive sign, it's got a value associated with it as well. What about a neutron? No charge, yep, neutral. And then the electrons are those counterbalancing negative charges, right? And again, not just negative, but a charge of -1 for each one of those electrons. All right, so we got our anatomy of an atom here. Atoms are composed of three subatomic particles, protons, neutrons, electrons. The protons and the neutrons live in the middle of the atom. The electrons are zipping around on the outside. The middle of that atom has all the mass of that atom. And then the charge of the protons positive in the middle, and the electrons that are decorating the outside are all negatively charged. Cool. All right, so let's look at our periodic table. Everybody flip over that page that we were just looking at. Here's your periodic table. This is our periodic table for the course. Every periodic table differs ever so slightly, specifically that the number at the very bottom, and it's important to be consistent when you're designing a course. So this is the periodic table that I built my course around. So whenever you're doing your homework, you need to make sure to use this periodic table here. Okay? Cool. All right. And what is the periodic table? So the periodic table is essentially a summary of all the different atoms that human beings have discovered here on Earth. All right? If we go and zoom in on each one of these tiles, let's pick apart these tiles here. The very top number is what's called the atomic number. And the atomic number actually has a very important meaning. First of all, let's just note that the periodic table is organized from in order of increasing atomic number. It's kind of got this weird zigzaggy shape to it, and we'll discuss why that zigzaggy shape exists. But generally speaking, when you read it from left to right, it goes 1, 2, 3, 4, 5, 6, 7, 8, right? All of these elements are organized in increasing atomic number, okay? And again, that atomic number has a very important meaning. Does anybody remember? The atomic number corresponds to the number of what in that atom? The number of protons, all right? So what makes an atom a specific element is the number of protons it contains. The number of protons that live in the nucleus of that atom will specifically tell you what type of atom you're talking about. We give each one of these elements a name. And then, like all scientists, we're super lazy, and every time we're trying to talk about boron, we don't want to have to write the word boron, so we also give it a little symbol. And then the last number on this periodic table is one that we will actually utilize quite a bit in this course. This is what's called the average atomic mass. All right, it's also called the molar mass. We'll sort of graduate to that definition here in a bit, but right now we're going to call it the average atomic mass, and we're going to return to that towards the end of the lecture. Okay? But again, importantly, what makes boron boron is the fact that that atom, if I'm holding a boron atom in my hand, what makes it boron is the fact that it has 5 protons. If I take a proton away, it is no longer boron. Now it's going to be beryllium. Right? The number of protons will uniquely point you to one of those tiles on the periodic table. Okay? Now, not all boron atoms are created equal. All right, let's take a look at these 3 atoms here, and we're going to label this section isotopes. All right, so we got this atom here. Let's figure out, we have 1, 2, 3, 4, 5, 6 protons in this atom. So which element must I be talking about if I'm talking about an atom that has 6 protons? Carbon. Okay, so let's just name it up here. Okay, if we just want to continue, we have 1, 2, 3, 4, 5, 6 of these neutrons, and we also have 1, 2, 3, 4, 5, 6 electrons in this particular atom. All right, but again, the number of protons is how I know that we're talking about carbon. Let's move on to the next one. Again, we have 1, 2, 3, 4, 5, 6 protons. So again, I'm talking about carbon. But now if I count the number of neutrons that I have in the nucleus of this atom, I have 1, 2, 3, 4, 5, 6, 7 neutrons. Both of these atoms are carbon atoms. It has to be because they have the same number of protons. But they differ in the number of neutrons. This is what we would call a pair of isotopes. So isotopes have the same number of protons, same element, but they differ in the number of neutrons. Sorry, give me a second. Let me rewrite this up here. Again, same number of protons. Different number of neutrons. Okay. So, we want to be able to, if we're talking about one of these isotopes or the other, we kind of have to have a different name for it. So now we're going to introduce what's called a mass number. Jeez Louise. So each isotope is given a mass number, and that mass number is simply the number of protons in that atom plus the number of neutrons. Okay, so let's do this first one here. We have 6 protons and 6 neutrons. What would be the mass number of this particular atom? 12, right? The sum of the protons plus neutrons gives you your mass number. So if I was trying to talk about this specific atom right here, I can't just call it carbon. I'm going to call it carbon 12. All right, so we name specific isotopes with the name and then a dash and then that mass number. Okay, if we looked at our last example here, this one has 6 protons and 8 neutrons. I want you to finish naming these 2 atoms here. This middle one has a mass number of 13, so that would be the carbon 13 atom. And the last one would have a mass number of 14, and that's the carbon 14 atom. Okay, so it turns out that if you gathered all the carbon in the world, it would be one of these 3 atoms that you have here. And it turns out that actually the vast majority of carbon is this carbon 12 atom right here. But there is a little bit of carbon 13 and carbon 14 out there as well. All right, so these are all the different isotopes of carbon that exist. And you can't tell just by looking at the periodic table what isotopes an element has. Big brain scientists got in there somewhere and measured how many of these atoms exist. All right, so that's not something that you tell just by looking at the periodic table. All right, so in addition to the name of the isotope, we also have a little fancy way to abbreviate an isotope symbol. Okay, these have this kind of same basic format. Where first you have your chemical symbol. And then they've got these 2 little numbers on there. We got a superscript and a subscript. The superscript is the mass number of that isotope. And the subscript is simply the atomic number. There are very many sources where you will see that atomic number subscript omitted because it's a redundant piece of information. If you know the chemical symbol, you already know what its atomic number is. But our textbook uses this format, so this is the format we're going to stick with here. Okay? So just to go an example here, if we look on our periodic table, the symbol for carbon is just that uppercase C. I got to put the mass number in the upper left-hand corner, so that's carbon 12. And again, in the lower left-hand corner is going to go that atomic number, the number of protons, 6. So see if you can't finish the symbols for these other 2 isotopes that we're looking at here. So this one would be carbon 13 with a 13 up top. This one would have a 14, but they would all share that same 6 subscript because that is the atomic number of carbon. Okay, so we got the name of our isotope as well as kind of this abbreviated way of representing that isotope. Okay, and then lastly, last thing that we can talk about is the charge, or what we would call the net charge on that atom. If we look, actually all 3 of these examples have 6 electrons, so let's just focus on this one here. Remember, the protons are positively charged, and I got 6 of them. So that means that in the center of this atom, I have a total charge of +6. But then I have these electrons on the outside, and each electron has a charge of -1, right? So the positive charge in the middle in this example is canceled out by the negative charge on the outside. So the net charge of this particular atom would simply be 0. Okay, and again, they all in these examples have the same number of protons as electrons. But if I had more electrons than I did protons, then I would have an excess of negative charge, or what we would call a net negative charge. If I had fewer electrons than I do protons, then that atom would have a net positive charge. All right? We can determine the net charge on a particular atom. It's the number of protons minus the number of electrons. All right, and we can think about it like a math problem, but we're going to sort of talk about a little bit of a simpler way to get at this here. Okay, one more vocab before we move on. If it does have a net charge associated with it, we don't call it an atom, we call it an ion. An ion is an atom with a net charge. Simply meaning that there's an imbalance between the number of protons and the number of electrons. Cool. All right, we're going to summarize all this in what we're going to call an isotope table. All right, so we're going to make a table. We got the name of our isotope, the symbol, number of protons, number of neutrons, number of electrons. As well as those two new quantities that we discussed, the mass number and the charge. Okay. So the name of the game here is I'm going to give you certain pieces of information on this table, and you got to fill out the rest of it for me. All right? So we'll start with this. I am holding an atom in my hand that has 15 protons, 16 neutrons, and 15 electrons. All right? We're going to do this one together. So I need to get the name of this particular atom. Which one of those three categories am I going to use to get the name of my element here? Number of protons. The number of protons will uniquely point me to one of those tiles on our periodic table. So if we look here, which element are we talking about? Phosphorus. Phosphorus has that symbol with that uppercase P. Okay? But I'm talking about a specific isotope of phosphorus, right? I gave you a specific number of neutrons that were in this. So let's figure out what the mass number of this atom would be. How do we get mass number? Which two categories do we look at? Right? So if I'm trying to find my mass number here, I need to add the number of protons to the number of neutrons. All right, so 15 plus 16 gives me that mass number of 31. So everybody take a second and complete the name and the symbol here, right? We have to include that information in our name and our symbol. Not just phosphorus, phosphorus 31. And the symbol has that little mass number in the top and the atomic number in the bottom. Okay? Now, for net charge, you can think about it like a math equation, but honestly, it's kind of easy to get tripped up. So let's just take a step back and see if we can do this without plugging in numbers here. We have 15 protons and 15 electrons, the same number of protons as electrons. So what's going to be the charge on this atom that we have? It's just going to be 0, right? The positive cancels out the negative, so we'll have this net charge of 0. Cool. I'm going to put down 2 more examples, and I want you to try to work through them on your own, and then we'll go through them together. All right, so if I'm going to do my symbol here, first of all, when you're first starting out, it's a real Where's Waldo game, trying to find elements on this periodic table. After you get some practice, you kind of get a sense of where things live, and it makes your life a little bit easier. But yes, the name of the game here is you just got to hunt down where the heck chromium lives. I will say also, generally speaking, we are mainly concerned with the first 4, maybe 5 rows on the periodic table. The other more larger elements are incredibly rare, and you will very rarely see them, all right? Cool. All right, so anyway, chromium, if we found it here, that would have how many protons? 24. That's element 24 on our periodic table. So then, based on that tile, I can also get that its chemical symbol is the Cr, and then I can finish off my symbol here, putting the mass number at the top and that atomic number down at the bottom. Okay. Let's skip number of neutrons for right now, and let's get to mass number. What would be the mass number of this particular isotope? 51, that's what the name tells us, right? When I tell you chromium 51, I'm telling you that the mass number is 51. Okay? And now we have to figure out the net charge. And you could totally use that formula that I gave you and plug in stuff. But again, it's kind of easy to maybe misremember the formula. So let's just take a step back. We have 24 protons and 22 electrons. We have more protons than we do electrons. So should our net charge be positive or negative? Positive, right? And that kind of take a step back approach will save you from making a really stupid mistake where you accidentally swap the two terms in your formula or something like that, right? And then in fact, I have 2 more protons than I do electrons, so that would be a net charge of +2, okay? Now, importantly, we got to update our symbol. This is something new here. Whenever we have an ion, remember we give that special name to atoms that have a net charge, we have to include that net charge in our symbol as well. And that goes in the top right-hand corner. Right? So this, if it has a charge, let's just look at these next to each other. Phosphorus, we didn't put anything because phosphorus in this example did not have any charge associated with it, or rather had a net charge of 0. But if there is a net charge, we have to include that in our chemical symbol. Okay? One more thing before we move on from charges in terms of notation. You will see both the charge with the sign and then value, or the value and then the sign. All right? Both of these are perfectly acceptable. There's some people that will tell you that this one's more correct in chemistry, and I feel like they're full of it. All right, and in fact, you will see me sort of default to this. This is a more mathy physics way of representing charges, and that's just more reflective of my education. So I tend to put the sign before the number, but it's totally irrelevant, right? Either order would be perfectly equivalent, right? These are perfectly fine answers. Cool. All right, so now we have one more box here, the number of neutrons. Okay, how am I going to figure out the number of neutrons? Which 2 other boxes am I going to look at here? The mass number and the number of protons. Exactly, because if you remember, we said that mass number equaled the number of protons plus the number of neutrons. And we used this formula to get our mass number in the previous example. Well, in this example, we don't know what that number of neutrons is. But we do have the number of protons, and we've already been given the mass number. And so just like any mathematical equation, as long as you only have one missing variable, you can do some algebra and rearrange to solve for that missing variable. All right, so just to be clear, in order to rearrange this, I would find that the mass number minus the number of protons would give me that number of neutrons. All right, so that's exactly what I'm going to do. I'm going to take my 51, subtract off the 24, and that's how I get 27 neutrons. All right, importantly, these 3 boxes right here are very closely linked together. Number of protons, number of neutrons, and mass number. Cool. All right, so then the last one is a little bit more tricky. I gave you the number of protons, the mass number, and the charge. And we got to figure out everything else. All right? So first of all, because I gave you the number of protons, I already pointed you to one unique tile on this periodic table here, which was who? Bromine. So right off the bat, we know we're talking about bromine. And specifically, we're given the mass number as well. So this is bromine 81. All right? We can do our symbol for bromine as Br. I got my mass number at the top, that atomic number at the bottom. And what else did we just learn I'm going to have to include in this symbol? The charge. All right, so I'm also going to put that -2 or 2- if you prefer in that top corner. Okay, so now I'm missing number of neutrons and number of electrons. For number of neutrons, we're going to have to play the exact same game that we just did. Right? Again, these 3 boxes right here, protons, neutrons, and mass number are all linked. So I can take my mass number and subtract the number of protons. All right, 81 minus 35. And that would give me my 46 neutrons. Cool. So now we got one more to go here, number of electrons. How am I going to figure out the number of electrons that are in this particular atom? The net charge, right? So in the same way that neutrons, protons, and mass number are linked, protons, electrons, and net charge are linked. All right, we got that net charge equals number of protons plus number of, whoops, not plus, minus number of electrons. All right, so likewise, we can rearrange this equation. It's a little bit more difficult algebraically, but I trust you all have those skills at this point. We would get number of protons minus net charge would leave us with the number of electrons. Okay, but again, let's not think about this as a math problem, and let's just look at the sign of that net charge. It has a net charge of -2, a negative net charge. So what does that mean? Should I have more electrons than protons or less electrons? More electrons, right? In fact, I need 2 more. So again, you can kind of save yourself a little bit of brain power by just paying careful attention to the signs. All right, so indeed I would need to have 37 electrons in order to complete my isotope table here. Cool? Wonderful. All right, so last thing we're going to do, we're going to revisit this number here, this average atomic mass. Why the heck do we call it the average atomic mass? Well, remember, we were looking at those different carbon atoms, and those different carbon atoms had a different number of neutrons. And remember, all of the mass of an atom is in that nucleus, the protons and the neutrons. So this average atomic mass is telling you if you took a scoop of carbon, which contained all those different isotopes, on average, this would be the mass. Okay? All right, so now we're going to get this number going kind of in the opposite direction. Okay, and for the sake of instruction here, we just discovered a new element. We're going to give it the symbol X. And this element has exactly 2 isotopes. The first one is X51. And that has a mass of 51 AMU. Now, truthfully, isotope masses do not match exactly their mass number, but they're always very, very close. Okay, so typically this number would really be like 50.995, blah, blah, blah. It'd have a bunch of decimals. But for the sake of kind of easy math here, we're going to leave it at this nice round number. All right, the other isotope is X53 with a mass of 53 AMU. Oops. Cool. All right, so let's just build a little table here summarizing. We have our name. We have our mass, and we're going to leave one more category here as well. Okay, so we discovered this element in a mine somewhere, I don't know. And then we went through and we counted how many, or rather measured how many of those atoms were isotope 51 and how many were isotope 53, what we would call the percent abundance. Okay, and when we measured it, it turned out that 25% of all element X is that isotope 51. Okay? So, what would be the percent abundance of the isotope 53? So, how do I know that it would be 75? What do these two have to add up to? They have to add to 100. And that's because of one key piece of information that was given to us in the problem, that this element has only two isotopes. So if one of them's 25%, all the rest of it has to be the other isotope, right? So I can figure that out because they must add, if you have all of your isotopes, they must sum to 100%. So absolutely. What's up?
If they have equal amounts of protons and neutrons, is that an isotope, or is it only when there's more or less neutrons?
No. It's not about the ratio of protons to neutrons within the atom. It's two atoms that have a different number of neutrons, right? So for example, when we looked at these two isotopes, that first one had the same number of protons and neutrons. That's just luck. No, an isotope, you have to have two to be like a pair of isotopes, right? When you're comparing two things, they're two atoms that have the same number of neutrons, but same number of protons, but a different number of neutrons. If we say that we're talking about an isotope, it means that we're talking about a specific number of protons and neutrons. But they don't have to be equal. They could be more or less, or there's no relationship between the number of protons and neutrons, at least not in this course. All right. Okay, so now lastly, we want to complete our periodic table. We got our symbol, but now we got to determine that number at the bottom here, that average atomic mass. And we're going to do that using the data table above. All right, I'm going to abbreviate this AAM for average atomic mass. It's going to be equal to the sum of the mass of each isotope multiplied by its percent abundance. Okay, this fancy little E here means the sum of all of your isotopes. You take all your isotopes, multiply the mass by the abundance, and sum them all together. All right? The only caveat here is we have to put that percent in what's called fraction form. Percents are something that we as humans got used to, and I kind of blame it on the retail industry getting us all used to this 50% off sale and all that. But anytime you use that piece of information in a math problem, you always have to convert it back to a fraction. Okay? So how do I get 25% in fraction form? So first of all, what would 25% be in fraction form? 25% is 0.25. So the percent divided by 100. That's how you get to fraction form. All right, so then if we're going to do our calculation, and I'm going to write it all out here, our average atomic mass is the mass of that first element, first isotope, 51 AMU, times its abundance in fraction form, 0.25. And again, we got that fancy uppercase sigma here, meaning the sum. So now I have to add on my other isotope. So now I'm going to say plus the mass of that isotope, 53, times the 0.75. Okay, and if we punch that all into our calculator, the average atomic mass would be 52.5. The nice thing about these two types of problems is we're not going to worry about sig figs. However, I do need to worry about my units here. What would be the units of this mass? AMU. That is atomic mass units. So if I was going to build my periodic table to include this new element, the number that would go at the bottom would be that average atomic mass, right? That 52.5 that we just calculated. All right. So again, if we look at our periodic table, we have this bottom number here for each one of these tiles. That corresponds to the average atomic mass. That means that they took all those boron atoms that existed and they did this weighted average accounting for how many boron 10s they had and how many boron 11s, and this was the average mass that you get. Cool? All right, cool. All right, we'll stop there and then we'll meet again for lab right after I take attendance.